Hello, thank you for the invitation to present at this workshop. My name is Howard Curtis from Ryder Geotechnical, and I'll be presenting scale considerations for offshore floating wind farms. Firstly, I present here an image of possible infrastructure for the electrical cable and mooring pile layout for a floating offshore wind farm. You will note that the mooring lines extend through the water column until they touch down at seabed and then connect to the mooring pile. And the electrical cables also extend down through the water column and may be restrained at some point with near seabed structures such as gravel bags or mattresses. And you'll note that the mooring piles and the secondary protection for the cables both protrude at a small height above seabed, which can potentially be affected by a scour. And I wish to just give you a bit of an overview with regards to mooring piles. So when does scour become a risk? So a seabed can be described as mobile if the seabed soils are granular with little or no cohesions, such as sand or coarse silts, and generally in shallow waters where seabed currents are high, or where significant wave heights induce near seabed currents. And when a structure is installed at the seabed, scour can occur around the structure due to the structure's impact to the hydrodynamic flows. So a commonly used relationship between current speed and particle size is presented in this slide. This is referred to from Salisbury and many other references. And as the current speed increases, larger particles are mobilized. So for example, a current speed of 1.2 meters per second is able to mobilize particle diameters up to 2 millimeters, and particles larger than 2 millimeters may remain stable. When we look at typical monopile scale considerations, we can see here with the transition piece, the yellow block at sea level, with the monopile installed into the seabed, the brown area. If the site is mobile, then the scale depth can be calculated based on particle size distribution, current velocity, angularity, and water depth, and is typically in the region of between 1 to 2.4 times the pile diameter. And the lateral extent of the scour is a relationship compared to the angular response of the sand. And once this is determined, developers typically choose to place a gravel blanket over the entire area to prevent scour from happening during the design life of the wind turbine. When we move on to offshore floating wind, mooring piles may be used, such as that shown in this image. There's two types of mooring pile configurations. The first is where the cables are mounted to the top of the mooring pile, and the second is where the mooring lines are attached to the side of the mooring pile. And as mooring piles are installed, the soil becomes trapped within the void of the pile, creating heave at the top of the pile, and therefore the pile head comes to rest at a height above seabed. This may cause some disruption of the hydrodynamic flows around the pile, and therefore scour can become a risk. However, because there is not a infinitely long foundation in the water column, the 1 to 2.4 times D no longer applies, and the scour extent may be greatly reduced, and potentially the requirement for installing gravel blankets are also reduced. And since the vertical extent of the scour may be reduced, there may be an option to reduce capacity as opposed to installing gravel blankets. Then when we look at mooring piles loaded at depth below the seabed, the capacity in this scenario is much greater, since the efficiency is higher when loading the pile at depth, because it mobilises more of the soil strength. However, there is risk of the oscillations of the mooring lines causing propagation of scour around the mooring lines until the trenches develop all the way to the pile. And this is obviously an extreme case and involves complex wave structure and soil interaction. But if this can be properly understood, appropriate mitigation measures can be implemented, such as restraining the mooring lines, installing gravel blankets at a smaller extent, or perhaps optimising the pad-eye depth. So as we look towards installing floating offshore wind farms in greater scale, these sites are typically in water depths of between 50 and 100 metres, or even more in some areas of the world. And for top-loaded mooring piles, modelling is required to determine the scour potential and its vertical extent to hopefully reduce the requirement of gravel blankets. And to enable the use of side-loaded mooring piles, the modelling is required to fully understand the cable trenching mechanism. Mooring piles are proven technology for oil and gas projects, but the numbers of piles required for offshore wind farms justifies improved understanding of the modelling techniques. If you have any questions, I'll look forward to answering them. Bye for now.